We've gotten a good sense of differential equations and how to solve them by looking at first-order differential equations. And we looked at linear first-order differential equations and nonlinear first-order differential equations. And now we're going to start tackling differential equations more broadly and go into higher-order differential equations, so greater than or equal to second-order differential equations. We'll primarily focus on second-order differential equations, but there is a general theory for linear differential equations. And this is going to be our concern for now, is to focus on linear differential equations. And before walking into the theory for linear differential equations, we're going to do a scandalously short excursion into linear equations in general. Okay, so what does linearity mean? What's the general idea? Because there is this essential core of what linearity means, regardless of the mathematical field, differential equations or systems of equations, and so on. And we're going to isolate that aspect or get a sense of it prior to jumping into the differential equations, and then the results of linearity in differential equations will make much more sense. So suppose we have this system here, okay? And one very broad question we could ask is, when does the system of linear equations have a solution? And when is that solution unique? Okay, so we have here the two unknowns of x1 and x2, and you could just assume that these coefficients and these b's are real numbers. Well, these equations are, you could see there is no x squared in here for the variables. And so you could rewrite this as in terms of a matrix equation, actually. Okay, so you could succinctly write these two equations into this system. Okay, and you can do this precisely because the system of equations is linear in the variables. Okay, and then the matrix equation looks like this, where A is this matrix there, x1, x2 is this vector, we call this a vector, and B is also this vector. So we're asking which vector x, when you operate with the matrix A, gives you B. And notice something about matrix operations in general, okay? A linear operation will have that L, you basically have two major conditions. L operating on x, the vector x, and the vector y is equal to L operating on the vector x plus L operating on the vector y. Okay, this would be the case with the matrix there. Okay, that's how matrix multiplication works. Okay, and why we could represent many linear operations in terms of matrices. And the second major condition is that L operating on a vector times this constant A is the same as multiplying the constant A times the operation on the vector x. So basically, scalar multiplication commutes with the linear operator, and addition commutes with the linear operator. Okay, these look like very simple, humble kind of conditions, but they define linearity. They're essential aspects of linearity. This is true for matrix operations, and so as we'll see with differential equations, they will have very broad consequences. Okay. Okay, so focusing on a particular example here, we have that system there. We rewrite it as a matrix. It's a linear equation, so we could linear system, so we could rewrite it as matrix. And this has the unique solution 1, 1. Now, what does that mean? Okay, what does it mean that there is this unique solution? Well, you could represent x plus y equals 2, this first equation, as this blue line over here, okay? And you could represent x minus y equals 0 as this pink line over there. And a unique solution is basically asking where these two lines intersect. And we found the unique solution 1, 1. Alright, so let's take a look at another example. So focus on this right here. Notice that the first equation, x plus y equals 1, has a similar form to the second one. In fact, the second equation is 2 times the first equation. Okay? And are you getting more information when you take an equation and you just multiply by 2? No. I mean, if the previous equation was true, then the next one is true. You're not giving more information to the system. Okay? And this here should be a negative 1 there, up there. Okay? What you're basically getting here is infinitely many solutions. Any solution that looks like C1 minus C will, for any C, so you could take like 0, C equals 0, and you'll get that x equals 0 and y equals 1, or you could take C equals 1 and you'll get x is equal to 1 and y is equal to 0. All of those work. Graphically, this means that both of those equations, you know, they're basically the same line, okay? So orange and pink, and they're exactly the same line. They intersect each other everywhere because they're the same line. You didn't add any new information there, okay? In some sense, that this second equation is not independent from the first. And finally, we could look at this last equation here. And this has no solutions, okay? One equation is offset. So here's x plus 2y is equal to 1, and here's x plus 2y equals 0. They're not exactly drawn to scale, but you get the idea that they never intersect, okay? So above there is just a broad view of linear equations and what their solutions mean. We could then ask the next, and this is the more important question for our purposes, when does a set of vectors uniquely represent any other vector? Okay? So if I have a set of vectors u and v, okay, can I write all my vectors as a constant multiple of each vector summed with the other one? Okay, so this relation that you see there. And if I can write a vector this way, is it uniquely represented? So is there only one C1 and one C2 that would that I could represent the vector x with? Okay, so that's the other major question here that we could ask with linear algebra. Okay, and it turns out not to be independent from that first question of just solving linear equations, because if you have this vector x, okay, and you want to write it in terms of the two vectors u and v, then you could rewrite this right hand side. Okay, what are you solving for here? You're not solving for x and y as we were doing above, but solving for C1, C2, okay? And so you could rewrite this right-hand side as this matrix equation, and you know, this plays now the part of B above, and this plays the part of the vector above, okay? And so you're down to the same place, okay, of solving a matrix equation. Okay? And if you take a look, the standard bases vector, okay, 1, 0, and 0, 1, does give us a unique representation. So any vector in R2, okay, if you're looking at R2 here, okay, which is just the standard vector space with two free components, then 1, 0, and 0, 1 do give you a unique C1, C2. Okay, any vector, like let's just choose a random one to kind of get a sense of what's going on. Say I have this vector 2, negative 1. Well, then I could just choose 2 times 1C and minus 1 times 0, 1. And so you see this vector here and this vector here. Okay, and 2, negative 1 cannot be represented by any other constants than 2 and negative 1 there. Okay, so there is a unique representation with these two vectors, and we call this the basis. Okay, for differential equations, we're going to be, you could think about the basis as kind of the fundamental set. Okay, just to throw out a term there to give you a sneak peek of what's going to go on. This isn't, so even though this is the standard basis vector, okay, you could also use these. These two vectors also give you a unique representation of each vector in R2. And they represent all vectors in R2. So you could represent any vector in R2 uniquely with this. And so we say it spans R2 when you could represent any vector using that basis. Okay? And this works because this vector and that vector are linearly independent. Okay? And we're going to make this formal for functions, what linear independence mean, but just to kind of give you a idea here, you can't represent, this vector is not just a constant multiple of that other vector. Okay, so in this simple example, that's how we could think about it. The same with these two. They have independent information in them. They point in different directions. Okay, that's the crucial part of linear independence. They're not just a multiple of the other. They literally point in different directions. This, for example, points in the plus x direction, this in the plus y direction, and so they have independent pieces of information. These two vectors, okay, if you notice here, this is same as the matrix that we did, based on how we create our matrix from using these basis vectors. Okay, so 1, 1 and 2, 2. That's gonna look like this when we write it out in terms of a matrix. Do not span R2. And notice that 1 is just a constant multiple of the other. Okay, this second vector is just 2 times this first vector. So they don't have independent information. Neither do these are the same vector. Okay, it's not even a constant multiple. Okay, these two vectors would give you that matrix. All right, so you don't have, what's crucial here, the big takeaway, and you could ask, when does any of these equations, any of these matrix equations have unique solutions? Any of them above that we looked at, just more broadly. This matrix equation has a unique solution if and only if the determinant of A does not equal 0. Okay, so that's one major key takeaway, and for our purposes, this is going to look like a condition on what's called the Wronskian. Okay, we'll learn more about that. And another key takeaway here is the relation between information and span. Okay, you got to develop this sense. These two vectors and these two vectors, they don't have additional information. Obviously, this here is the same information, right? And this here is just 2 times that first vector. That's not adding anything new, okay? You just take a vector and multiply it by a constant. It's still pointing in that same direction. Whereas these vectors, they have different information in them, okay? And this is why we were able to get a unique solution here. We have different information that's consistent. Down here we had different information that's inconsistent, okay? And so these are the key takeaways. This idea of, what does information in span mean here when we have different information, two different pieces of information, we could span R2, okay? And that the determinant of A not equal 0 gives you a unique solution. So this is just very broad looking at linear equations, and we will be using this for differential equations.